NORA CMOS logic, NP-Domino logic. In domino CMOS logic gates, all logic operations are performed by the NMOS transistors acting as pull-down networks, while the role of PMOS transistors is limited to. Here you can see the figure NORA CMOS logic consisting of alternating NMOS and PMOS stages and the scheduling of precharge evolution phases. Precharging the dynamic nodes as an alternative and a complement to a NMOS based domino CMOS logic, we can construct dynamic logic gates using PMOS transistors as well. Consider the circuit shown in figure with alternating NMOS and PMOS logic states. Note that the precharge and evaluate timing of NMOS logic states is accomplished by the logic signal phi, whereas the PMOS logic stages are controlled by the inverted logic signal phi dash. The operation of the NORA CMOS circuit is as follows. When the clock signal is low, the output nodes of NMOS logic blocks are precharged to VDD through the PMOS precharge transistors, whereas the output nodes of PMOS logic blocks are pre-discharged to 0 volts through the NMOS discharge transistors driven by phi. When the clock signal makes a low to high transition, note that the inverted clock signal phi dash makes a high to low transition simultaneously. All cascaded NMOS and PMOS logic gates evaluate one after the other, much like the domino CMOS examined earlier. A simple NORA CMOS circuit example is shown in figure. The advantage of NORA CMOS logic is that a static CMOS inverter is not required at the output of every dynamic logic stage. Instead, the direct coupling of logic blocks is feasible by alternating NMOS and PMOS logic blocks. NORA logic is also compatible with the domino CMOS logic. Here you can see the figure NORA CMOS logic circuit example. Outputs of NORA NMOS logic blocks can be inverted and then applied to the input of the domino CMOS block, which is also driven by the clock signal phi. Similarly, the buffered output of a domino CMOS stage can be applied directly to the input of a NORA NMOS stage. The second important advantage of NORA CMOS logic is that it allows pipeline system architecture. Consider the circuit shown in figure A, which consists of an NMOS PMOS logic sequence similar to the one shown in figure and a clocked CMOS C-square MOS output buffer. It can be easily seen that all stages of this circuit perform the percentage discharge operation when the clock is low, and all stages of the circuit evaluate output levels when the clock is high. Therefore, we will call this circuit a phi session, meaning that evaluation occurs during active phi. Now consider the circuit shown in figure B, which is essentially the same circuit shown in figure A, but with the only difference being that the signals phi and phi dash have been interchanged. In this circuit, all logic stages perform the pre-charge discharge operation when the clock is high. When the clock is high, and all the stages evaluate output levels when the clock is low. Therefore, we will call this circuit a phi dash session, meaning that evaluation occurs during active phi. A pipelined system can be constructed simply by simply cascading alternative phi and phi dash session as shown in figure C. Note that each of these sessions may consist of several logic stages, and that all logic stages in one session are evaluated during the same clock cycle. When the clock is low, the phi sessions in the pipeline system undergo the pre-charge cycle, while the phi sessions undergo evaluation. When the clock signal changes from low to high, the phi sessions start the evaluation cycle, while the phi sessions undergo pre-charge. Thus, constructive sets of input data can be processed in alternating sessions of the pipeline system. As in all CMOS structures, NORA CMOS logic gates also suffer from charge sharing and leakage. To overcome the dynamic charge sharing, the soft node leakage problems in NORA CMOS structures, a circuit called zipper CMOS can be used. Here you can see in this figure a NORA CMOS phi session evaluation occurs during phi equal to 1. B. NORA CMOS phi session evaluation occurs during phi equal to 0. C. A pipelined NORA CMOS system. Zipper CMOS circuits. The basic circuit architecture of zipper CMOS is essentially identified to NORA CMOS with the exception of the clock signals. The zipper CMOS clock scheme requires the generation of slightly different clock signals for the pre-charge discharge transistors and for the pull down pull up transistors. In particular, the clock signals which drive the PMOS pre-charge and NMOS discharge transistors allow these transistors to remain in weak conduction or near cutoff during the evaluation phase, thus compensating for the charge leakage and charge sharing problems. The generalized circuit diagram and the clock signals of the zipper CMOS architecture are shown in figure. As you can see in the figure, general circuit structure and clock signals of zipper CMOS. True single phase clock TSPC dynamic CMOS. The dynamic circuit technique to be presented in the following is distinctly different from the NORA CMOS circuit architecture in that it uses only one clock signal which is never inverted. Since the inverted clock signal phi dash is not used anywhere in the system, no clock skew problem exists. Consequently, higher clock frequencies can be reached for dynamic pipeline operations. Here you can see a pipelined true single phase clock CMOS system. Consider the circuit diagram shown in figure. The circuit consists of alternating stages called N blocks and P blocks, and each block is being driven by the same clock signal phi. N block is constructed by cascading a dynamic NMOS stage and a dynamic latch, while a P block is constructed by cascading a dynamic PMOS stage and a dynamic latch. While the circuit signal is low, the output node of the N block is being precharged to VDD by the PMOS precharged transistor. When the clock signal switches from low to high, the logic stage output is evaluated and the output latch generates a valid output level. On the other hand, we can see by inspection that the P block pre-discharges when the clock is high and evaluates when the clock is low. This means that a cascade connection of alternating N block and P block circuits as shown in figure will allow pipeline operation using a single clock signal. Compared to NORA CMOS, we need 2 extra transistors per stage, but the ability to operate with a true single phase clock signal offers very attractive possibilities from the system design point of view. Figure shows the circuit diagram of a rising edge triggered D-type flip-flop DFF, which is constructed with the TSPS principle. The circuit consists of 11 transistors in 4 simple stages. When the clock signal is low, the stage acts as a transparent latch to receive the input signal, while the output node of the second stage is being precharged. During this cycle, the third and fourth stages simply keep the previous output stage. When the clock signal switches from low to high, the first stage ceases to be transparent and the second stage starts evaluation. At the same time, the third stage becomes transparent and transmits the sampled value to the output. Note that the final stage inverter is only used to obtain the non-inverted output level. Here you can see in this figure circuit diagram of a TSPC based rising edge trigger DFF. In this figure you can see mask layout of TSPC based DFF circuit. The mask layout of this circuit using 0.8 nanometer CMOS technology design rules. Micrometer CMOS technology design rules. Is shown in figure. The device dimensions are WL and 2 micrometer by 0.8 micrometer for NMOS transistor and WLP 5.6 micrometer and 0.8 micrometer for PMOS transistor. The layout parasitics are determined through circuit extraction, and the extracted circuit file was stimulated with SPICE to determine its performance. The simulated input and output waveforms of the TSPC based DFF circuit are given in the figure. It can be seen that the circuit is capable of operating with a clock frequency of 500 MHz with their relatively simple design. Low transistor count and high speed. The TSPC based circuits offer a very favorable alternative, very favorable to conventional CMOS circuits, especially in high performance designs. Here you can see in this figure simulation results showing the operation of TSPC based DFF circuit with clock frequency of 500 megahertz. Thank you.